Hi everyone, this is Ramagiri Kiran, working as assistant professor in the Department of Electronics and Communication Engineering at Marri Reddy Institute of Technology and Management, Dundigal, Hyderabad. Today we are going to discuss on the subject digital electronics. In the last class, we have taken types of conversions. In that one, we have completed 6 types of conversions. Remaining 6 types of conversions we will continue now. Decimal to binary conversion. Decimal to binary conversion. In this method, the integer part of the given decimal number to binary is successfully divided by 2 and the fractional part is successfully multiplied by 2. Example, for the integer part, 165 divided by 2. 2 8 is 16, 2 4 is 2 and the remainder is 1. 2 4 is 8, 2 2s and the remainder is 0. 2 2s 4, 2 1s are 2 and the remainder is 0. 2 1s are 2, 2 10s are 20, the remainder is 1. 2 5s are 10, remainder is 0. 2 2s 4, remainder is 1. 2 1s are 2, remainder is 0 and the final result will be 1 0 1 0 0 1 0 1. This is for integer part. 165 is nothing but we will having the integer part and fractional part 0.75. Then multiply with that with 2. 0.75 into 2 you will get 1.5. Then remainder will be 1. Then 0.5 into 2 will get remainder is you will get 1.0. Remainder will be 1. Then final result for 0.75 is 1 1. Then final result is 101 00 101.11 to the base 2. This is the final result for binary. Decimal to octal conversion. In this method, the integer part of the given decimal number to octal number is successfully divided by 8 and fractional part is successfully multiplied by 8. In the integer part, the remainders read from top to bottom and gives the integer part of its binary equivalent, and the fractional part, the carrier read from top to bottom gives the fractional part of the binary equivalent. Here consider one example, 55.25. 55 divided by 8. 8 6 are 48. The remainder will be 7. Then the final result will be 6 7. And this is for integer part. And for fractional part, 0.25 into 8 will get the result is 2.00. Then final result for 55.25 to the base 10 equal to 67.2 to the base 8. 67 is nothing but we will call as an integer part. 0.2 is nothing but we will call as a fractional part. That is the final result for decimal to octal conversion. Next one is decimal to hexadecimal conversion. In this method, decimal to hexadecimal conversion. In this method, the integer part of the given decimal number to hexadecimal is successfully divided by 16 and the fractional part is successfully multiplied by 16. In the integer part, the remainders read from bottom to top gives the integer part of the binary equivalent, and the fractional part of the carrier read from top to bottom gives the fractional part of the binary equivalent. Example 55.25. 55 is nothing but an integer part. 55 divided by 16. 16 3 is 48 and the remainder will be 7. That is for 37 for the integer value. Then 0.25. Next fractional part 0.25 into 16 will get 4.0. Then final result for 55.25 to the base 10 equal to 37.4 to the base 16. That is the result, final result for hexadecimal. Next conversion is hexadecimal to binary conversion. Write the hexadecimal number. First step. Second step. Replace each hexadecimal digit with its 4-bit binary equivalent. Combine the binary groups. Example for this hexadecimal to binary is 2a to the base 16. Converting that into binary. Here in hexadecimal, a value is nothing but a 10. 2 in a 4 bit we can write as 0010. For a we can write as 1010. Then the final result for 2a to the base 16 equal to 00101010. That is your final result for binary conversion. Next conversion is hexadecimal to octal conversion. Convert each hexadecimal digit to its equivalent 4-bit binary. Make groups of 3 bits each of the binary obtained binary number digits into sets of 3 from right to left. Converting each 3-bit binary group to its equivalent octal number. Example is 3a. 3 which can be written as 0011 and a can be written as 1010. Then combining that into 3 bits from right to left. Then 010 which can be written as in decimal is 2. 111 which can be written as in decimal 7 and 000 which will be as 0 only. Then the final result for 3a to the base 16 equal to 7 to the base 8. That is the final result for hexadecimal to octal conversion. Next conversion, hexadecimal to decimal conversion. In this method, the integer part of the given decimal number to hexadecimal number is successfully divided by 16 and the fractional part is successfully multiplied by 16. In the integer part, the remainders read from bottom to top and gives the integer part of the binary equivalent, and the fractional part, the carrier read from top to bottom gives the fractional part of the binary equivalent. Example 1c 0.8 to the base 16. 1c is nothing but we can as integer part. 0.8 is fractional part. First calculating the integer part 1c, where in hexadecimal a value is 10, b value is 11, c value is 12, d value is 13, e value is 14, f value is 15. Here c value is nothing but a 12, 1.8, 16 power minus 1, 16 power 0, 16 power 1. 1 into 16 power 1 plus c into 16 power 0 equal to 1 into 16 power 1 is nothing but a 16. 1 into 16 power 1 is nothing but a 16. plus C. C is nothing but a 12. 12 into 16 power 0 is nothing but a 1. 16 plus 12 equal to 28. We got the integer part. Next, fractional part. 0.8. 8 into 16 power minus 1 is nothing but a 8 into 0.0625. 1 by 16. If we divide by 1 by 16, we'll get the 0.0625. Then the final result is you will get 0.5. Then integer part is 28 and fractional part is 0.5. This is the final result for decimal conversion. Next, binary number representation. Here binary number representation, here we are having two types. One is unsigned binary number and signed binary number. In unsigned binary, it represents only the positive numbers. Example 10, positive 10, positive 8, positive 3. Means 10 can be written as 1010, 8 can be written as 1000, 3 can be written as 0011. Only the positive terminals it represents. Negative terminals are invalid for unsigned binary number. For signed binary numbers, it contains positive 10 as well as negative 10. For positive 10, you will get 1010. For negative, we will get 1010 only. We can represent both positive numbers and negative numbers. Here for negative numbers, it can be represented in three ways. One is sign magnitude form, second one is one's complement form, third one is two's complement form. Here we will discuss first one, sign magnitude form. Sign magnitude form, where MSB is nothing but a most significant bit. MSB stands for most significant bit, represents the sign bit, and remaining bits represents the magnitude bit or actual binary. Example, if MSB equal to 0 for positive number, sign bit will be represented as 0, and the other bits represents the actual binary or we can call as magnitude. Example is 10, which can be written as 1010. Then the final result for this is nothing but a actual binary. If the MSB is 0, then this will get the final result for this 10. That is for MSB equal to 0 for positive number. If MSB equal to 1 for negative number, then MSB represents 1. Then remaining bits represents the magnitude or actual binary. Here for minus 10, we'll get 1 1 0 1 0, then represents with 1. That is nothing but for negative binary number. One's complement form. One's complement of a binary number is obtained by changing all zeros to ones and zeros to ones and ones to zeros. Example 1010. 0 becomes ones becomes zeros and zeros becomes 1. 1 zeros becomes 0, 0 becomes 1. Then the final result is 0101 for 10. Next, 2's complement. 2's complement of a binary number is obtained by adding the 1's complement and then add plus 1 to the final result. Example 1010. 1's complement for this is 1010, 0101. Then add with plus 1. Then we'll get the final result for 2's complement. This is 1's complement. By adding plus 1, we'll get the final result of 10. 1 1 0. Carry will be 1. Then 1 1 0. Then this is your final result for 2's complement. And here these are the references books for the digital electronics. Thank you.